Hi everybody, Dr. White back again. Now we're going to be talking about transformations of two random variables. So the idea is we're in a bivariate situation and we do transformations on both those random variables at once in kind of a mixed way, and we look at the distribution of these transformations. So we're going to need to throw in some background for those of you who have not yet taken Calc 3 or aren't far enough along yet in Calc 3. So first piece of background is just partial derivatives. In Calc 3, you start studying functions of more than one variable, like this one here. So this function f here is a function of two independent variables x and y, and the rule is that when you get your x and y, you do that stuff to them. And so you start with two real numbers, and what comes out, that sum of products there, is one real number. So it's a function from R2 to just R. Okay, real value function of two variables. Well, functions of one variable had derivative, instantaneous rates of change. Functions of two variables have what we call partial derivatives, which are measures of how fast the function is changing if you change one variable a little bit but hold the other one fixed. And you'll go into more of the theory of it in Calc 3, but the way that you compute a partial derivative is, with respect to one of the variables, is just to treat the other variable like it was a constant and take the derivative with respect to the variable you want to take the derivative with respect to. Now, the way you would write, say, the partial derivative of f with respect to the variable x is with those little bent d's, which, and so I'm just going to call them do. So I'm going to say do f, do x. And that just means, more professionally, the partial derivative of f with respect to x. So how do you get it? You just look at the formula for f and you say, x is my variable, y is a constant. And so when you do that, then the x cubed is the only function of x in there. The rest is just a constant multiple, 5y squared. And so the constant multiple rule would give us 5y squared times the derivative of x cubed for that term. And the derivative of 2x would be a 2. The derivative of 5y is a 0 because y is a constant, so 5y is a constant. And everybody agrees the derivative of 17 would be 0. So it simplifies down to, whoops, there's a typo. Should be 15x squared y squared plus a 2. Okay. 15x squared y squared plus a 2. All right, what's the partial of f with respect to y? Well, in that case, the 5x cubed is like a constant times the derivative of y squared makes 2y, giving us this term. This time the derivative of 2x is a 0 because the 2x is like a constant. But the derivative of 5y would deliver us a 5. The derivative of 17 is still 0. And that comes down to 10x cubed y plus a 5. Okay, another little typo there. Okay, second bit of review will commence after I take a sip of coffee, which I must need because I'm committing such typos. Not typos, I'm not typing. What should we call them? Writers? So the second bit of review is the Jacobian. Suppose that f1 of two independent variables, x1 and x2, is some real value two variable function, and f2 of x1 and x2 is another real value function. And let's make a matrix of the partial derivatives. So these little square bracket doohickeys say make a matrix. And a matrix has rows and columns, and this one has 2 rows and 2 columns. And in the first row, you've got partial derivatives of f1. First with respect to x1, then with respect to x2. And then the second row has the partial derivatives of f2, First with respect to x1, then with respect to x2. And so it kind of makes sense, like 1, 1, row 1, column 1, 1, 2, row 1, column 2. Makes sense. Now, the determinant of a matrix is something you might have studied back in high school math, and you can take determinants of any square matrix at all, 2 by 2, 3 by 3, 4 by 4, whatever. The determinant for a 2 by 2 matrix is all you need to know about here, and it's actually real easy to do if you keep the picture of the matrix in mind. What you do is you take the product going down that diagonal, going down from right to left, take that product. There it is. And then you take the product of the other diagonal, so this times this, the one heading down to the left, and you subtract that off, okay? That determinant is called the Jacobian of f1 and f2. So in general, it'll be some function of your x1 and x2 variables. All right, so that's the bit of Calc 3 that you need to know about. Now here comes a Hawkens Theorem that's introduced in section 5.2. And it gets called the change of variables technique. It's basically it's the same kind of idea as the change of variables technique for dealing with one random variable, but this is how you deal with transformations of a bivariate scenario. So suppose that x1, x2 is bivariate of continuous type. And let's say its support is some particular subset of R2 just called S sub x. X isn't really anything here. It's just because I'm too lazy to write down x1, x2, and the book is too. And let's say its PDF is little f of x1, x2 on that support. And let's say that we come up with another bivariate random variable situation consisting of y1 and y2, where capital Y1 is some function u1 of x1 and x2, and capital Y2 is some function u2 of x1, x2. So the u1 and the u2 are both two variable real valued functions. And together we've got a transformation from one bivariate scenario to another bivariate scenario. So that second bivariate scenario is going to have a different support, okay? Call it S sub y. But suppose that when you map from one support to the other, like you take your x1, x2, and you map to u1 of x1, x2, u2 of x2, 1, x2. So you're mapping to your y1, y2. Suppose that mapping between supports is 1 to 1. So that means no two x1, x2 points ever map onto the same y1, y2 point. In that case, then you could back solve for the x1 and the x2 in terms of the y1 and y2. You could take the inverse function, as it were. You would be able to find some function, I'll call it nu1, of y1 and y2 that could get you back to the x1, and another function nu2 of y1, y2 that could get you back to the x2. And suppose you take the Jacobian of those two functions, nu1 and nu2. So you're looking at that little determinant of a matrix of partial derivatives. So, it's this. And so that Jacobian, let's call it capital J. So it might be some function of, y1 and y2. Then you can get the PDF, the joint PDF for the y1, y2 scenario. The book calls it little g of y1, y2. And what you do, it looks a lot like the change of variables in the previous section. You just go to your little f, and for the x1, you plug in whatever expression you got to back solve it. And for the x2, you plug in whatever y1, y2 expression you got to back solve for it. And then you got to multiply. Back in the previous section, it was the absolute value of the derivative of the inverse f of y. Here is the absolute value of the Jacobian. So the Jacobian is painfully like a derivative, like a full-fledged derivative. It's composed of these partial derivatives. Together, they make something that's like a full derivative. And that idea can be made more precise in advanced calculus. And anyway, that's going to be good for all the y1, y2s and the support of this new bivariate scenario. So if you have had Calc 3, you'll know about a change of variables theorem that helps you to find multiple integrals. This is just a special case of the change of variables theorem, where the functions that you're integrating are PDFs, instead of just any old functions at all. That's really almost the same theorem. So they don't prove this theorem in the book, in the textbook. And that's because they're just figuring that you're going to take something like Calc 3 eventually. And you'll see the proof of the change of variables theorem, and you'll be happy with that. So let's try an example. Let's say you got two independent gamma random variables. And one of them is gamma with shape parameter alpha, and the other is gamma with shape parameter beta, but they both have the same theta parameter. 1 over their rate is the same theta. So it's like you're waiting for alpha events when the average time between them is theta, and here you are waiting for beta events. If that would be the case if these were whole numbers, alpha and beta can be any positive real numbers. So you can stick them together to make a bivariate scenario. And because the x1 and x2 are supposed to be independent, then the joint PDF is just going to be the product of the PDFs for the x1 and the x2 multiplied together. And now we've memorized what a gamma PDF looks like. So the PDF, for this one, the x1, would be 1 over gamma of alpha, theta to the alpha also on the bottom, x to the alpha minus 1, e to the minus x1 over theta. And then similarly for the x2, so when you multiply them together, you could write it out all like that. And that works on for all positive x1s and x2s. So the support here is the support is the first quadrant. Now, suppose you're thinking, all right, what if I were like waiting for alpha plus beta events to occur? Wouldn't that be the same as like wait for alpha events and then wait for a further beta event? That would be, it feels like that would be the same as just x1 plus x2, okay? And suppose you got curious and got curious about like, what fraction of that total waiting time for the alpha plus beta events is spent waiting for the first alpha event? That fraction here, I'm calling it y1. And I might get interested in like, what's the distribution of that new random variable? So it's a transformation of the x1 and the x2, that fraction of waiting time for the first alpha event. It's a transformation of x1 and x2. And I could use the change of variables technique maybe to figure out its distribution if I could make the y1 be part of a bivariate scenario. But that would mean I need to introduce another random variable to make up the other part of the bivariate scenario. And so I just, and so this is kind of the clever part. It's like out of the air, as it were, you pull y2 to be this other transformation of x1 and x2, just the sum of the two. Now, the reason why somebody might pull that quote unquote out of the air is they're actually kind of thinking ahead to how you would back solve and apply the change of variables. And that just turns out, that choice for y2 turns out to be a convenient choice to make the back solving go well. Okay, so we're now down to looking into that new bivariate scenario. And if we can get its joint PDF, then maybe we could go ahead for the marginal to get y1. That's pretty much my strategy. So we need to do some back solving. We need to get like x1 in terms of y1 and y2, and we need to get x2 in terms of y1 and y2. And so like here's how we get the y's out of the x's. How would we get the x's out of the y's? Well, let's see. x1, what would it be? One way to think about it is to solve this equation right there for x1. And you would get y1 times x1 plus x2. But x1 plus x2 is y2. So there you go. x1 is y1, y2. So our inverting function, nu1, as a function of y1 and y2 is just y1 times y2. Okay, let's back solve for x2. You can see some scratching down here where I tried away and then decided that wasn't very good. Here's what I settled on eventually. Take that equation, solve it for x2, and you get y2 minus x1. Okay. Well, we just found x1. It was y1, y2. So there's our new 2 inverting function. So we just head and get the Jacobian. And so let's see, partial of nu1 with respect to y1. All right, well, here's nu1. Take the derivative with respect to y1. So it's like y1 times a constant, and all we're going to get left is the constant. And the derivative of y1, y2 with respect to y2, this time the y1 is like the constant. Constant times x gives you constant for derivative. So we get a y1. And working in similar ways, the derivative of this with respect to y1 turns out to be minus y2. And the derivative of this with respect to y2 turns out to be 1 minus y1. And so when you take the determinant, you do a y2 times a 1 minus y1 down the diagonal. And then you're supposed to subtract off y1 times a minus y2 down the other diagonal. And simplify that with some algebra, and you just come up with y2. Sorry. So now apply your change of variables to it. And so you've got to go back to your f, and you've got to stick in, instead of the x1 and the x2, you've got to stick in what they are in terms of y1 and y2. So you got to do it there, and you also got to do it back up here. And then you're also going to throw in an absolute value of the Jacobian at the end. And so you get like all this stuff. And notice the x1 plus the x2 was y2 all along. That was pretty easy to find. And then here's the x1, and here's the x2 like we found it. And here's the absolute value of y2. Okay, but what's the support of that? What is the support of this bivariate situation? Remember that y1, well, first of all, remember that x1 and x2 are both positive. So that means that y1 and y2 have got to be both positive. But there's something about y1, it's a little restricted. It's a positive over a positive plus another positive. So that ratio there can never be bigger than 1. And certainly, it's the y1 has got to be less than the x1, because it's x1 divided by something more than it. So the support for this new bivariate situation really is just this. And so you could graph it. Here's the y1 axis horizontal, the y2 axis vertical. And here's the line y2 equals y1. And if the y-coordinate y2 is bigger, that puts you above that line. And so you're in that like infinite triangle going on. Now, back to this Jacobian. Since the y2 is definitely positive, it's just equal to its own absolute value. So, I could really just drop the absolute value signs here, and I could like maybe stick the y2 somewhere else, like maybe inside of here. Well, maybe I could pull out the y2 alpha to the -1 and stick on a y2 with it, whatever. But I'll just think of it here as just going to be y2. Now, we got that PDF, so we could go for the marginal of capital Y1. All we got to do is integrate from -infinity to infinity the joint PDF dy2. And so set up that integral, I think, well, y2 has to be positive, so I'm really only going to integrate from 0 to infinity. And then I got my PDF. And I go ahead and I do the best I can to stick stuff together. So let's see. If I look at this, a y2 factors out of it. So y2 times a 1 minus y2, y1. And so I'll have a y2 to the beta -1 from that. And I've got a y2 to the alpha -1 from this other product. And I've got a y2 here. So that's alpha -1 plus beta -1 plus a 1, y2s. Which actually works out to alpha plus beta -1, y2s. Now I've got some y1s and some 1 minus y1s, and when I count them all up, there's that many of each of them. And there's still that e to the minus y2 theta sitting around. And there's still all that other mess. So it's this horrible integral. But at least some of it doesn't depend on y2, and so I can factor it out, because it's like a constant as far as that integration is concerned. So I factor all that stuff out. And I'm left with this integral. And so, like, the variable of integration is y2, power of y2 times e to minus power of y2. I could get that if I did integration by parts a bunch of times. But gee, that would only work if the alpha and the beta were whole numbers, so that I could like eventually get down to the integral of e to the minus y2 with my integration by parts. And if they're so like, but that would be uncool to do. Have to do that, and it would be impossible if alpha and beta are not whole numbers. So we got to look for another way. And, I stare at this, and it just kind of reminds me a little bit of the PDF for a gamma, because those are basically constant times variable to a number, e to minus variable over a number. And we're in that situation. And so I'm just going to very carefully throw on a gamma of alpha plus beta here and a theta of alpha plus beta to go along with this stuff. And of course, to do that, I'm going to have to multiply by a gamma alpha plus beta and a theta alpha, beta to the alpha plus beta, which as a constant I'll factor outside. So I haven't changed the expression I'm working with. But this stuff right here, that's the PDF of a gamma random variable where the shape parameter is alpha plus beta and the second parameter is still theta, being integrated over its support. So it must be 1. Wow. And so the only stuff left is this stuff, and there's some cancellation to help us out. And we come to this kind of nice, symmetric looking thing. Now that works for all the y's. And remember, the y's being x1 over x1 plus x2, they couldn't be more than 1. The support is just y goes between 0 and 1. Such a random variable is called a beta random variable. A random variable with this PDF is a beta random variable. So you're going to use 2 parameters to specify it. Definitely worth exploring the shapes of the beta family, because you get to vary these 2 parameters. You might get quite a lot of interesting shapes for the PDF over that 0 to 1 range. And we'll do that. Now, this little bit right here up at the top, this like second one that we threw on because it was going to make the back solving convenient as opposed to other choices we might have made. It seems like an appendage. But when we go back and we think about it, we think, you know, we could go for the marginal of y2. And what is y2? It's the sum of these 2 independent gammas, gamma alpha, gamma beta, both with the theta parameter. And, you know, remember, we're very suspicious, based on some intuitive arguments we made earlier, that ought to be a gamma random variable. It would be like the waiting time for alpha plus beta events. So, you know, if we went and computed the marginal for y2 here, then maybe we'd have a full-fledged math proof that the sum of independent gammas with the same theta is another gamma with that beta. And you wouldn't be relying on the waiting for events argument, which only applies anyway when the alpha and the beta are whole numbers. It would be like for everything. So that would be cool. And I'm not going to do it here, but you might want to think about seeing if you could do it. Do that same kind of integration that we just did. So the book does a ton of examples with change of variables technique. And I would suggest that you pay special attention to theorem 5.2, number 1. If you start off with U and V being chi-square random variables with R1 and R2 degrees of freedom respectively, and say they're independent, and say you take each one of them and divide by its degrees of freedom and then take the ratio, that new random variable has a probability density function that you can actually figure out with all of the change of variables calculus. And it's so important that it forms a new named family of random variables called the F distributions. And so it's given by 2 parameters, 2 degree of freedom parameters. It's really important in statistics applications. We won't be taking it very far this semester, but I want you to know it's there, so I want you to study that theorem and its proof. So when you're working with a transformation of 2 random variables, you can use the change of variables technique like we've been doing so far, or you can use the CDF technique like we do with one random variable. We need to try a couple more examples, and we need to make sure at least one of them uses the CDF technique so that you can see how that would work in a 2-variable situation. Why don't I do that in a separate screencast? This one here has gone on, I think, probably long enough. See you later.